video is Unit 1, Learning Targets 7 through 9. And in this video, we will be talking about math and measurements and science. We won't be doing a lot of math in my class, but this is the time when we'll be doing some of it. Relatively easy stuff. Talking about the two systems of measurements that we'll be concerning ourselves with. The English system of measurement. This is our system. This is the system that we're used to. This is things like inches and feet, miles and acres, and those sorts of things. This is not used in science because there are too many different conversion rates and too many different odd things. It's largely based off the number 12, and it's not an easy number to deal with. And this is used by the great states or the great countries of, see the white countries here, the United States, of course, and then also down here you have Liberia, and then over here you have the country of Burma. Well, those are the countries that use this system. The rest of the world uses the metric system. Well, what is the metric system? What makes it nice and neat? Well, this is widely used in science. All conversions are multiples of 10. We learned to count by tens when we were in kindergarten. This is easy. This is used by most of the world. As you can see, the red is the metric system. The rest is not. This is things like meters and liters and grams. And here is a picture showing you how it's all based on 10. As you get bigger, it multiplies. As you get smaller, it divides. Now, with the metric system, science uses something in particular called the International System of Units, or that's often abbreviated as SI, because in French it's System International or something like that. And in the SI, there are 8 units. 7 here, but we'll be talking about eight different ones. And they are as follows. The A and the CD we won't be looking at in this class. First is mass, and the SI unit for mass is the kilogram. The mass of something is the amount of something. This is the amount of an object. How much of the object there is the mass. This is a kilogram. This is the standard by which all kilograms are based off of. It's kept in a nice airtight glass because if a little speck of dust lands on it, it's no longer a kilogram, and so it has to be protected. Now, when we begin talking about mass, let's make sure we understand that it's completely different than weight. Weight is the force of gravity acting on you. It's how gravity acts on you versus the amount of something. If you go to the moon, there's less gravity, so your weight will be less. However, your mass will not change. You will still have the same amount of you. You're not going to get smaller just because you go to the moon. You're just going to weigh less. Now, length. There's a picture of some standard length bars there. The SI unit for length is a meter, and length is obviously how long something is. We will be using centimeters in here instead of inches because we're going to use the metric system. Time, the base unit is a second, which doesn't differ from the English system. I have a picture here of this get-up, and this basically this measures what a second is, and it's the amount of time that it takes light to travel from one space to another space, and they do all this measurement in a device that looks like this. Temperature. Temperature, the base unit for temperature is Kelvin. Now, we won't use Kelvin a lot in here. Here's our friend Kelvin here. It actually is him. We will use Celsius. But to get Kelvin, you just add 273 to Celsius, which, again, we're not going to worry about in this class. If you take AP, we'll do some of those calculations. But the base SI unit for temperature is Kelvin. However, we will be dealing in Celsius in this class. And there's concentration. This is the amount of something in a particular volume. We'll be looking more at concentration in a further unit. The amount of something in a particular volume, you can see the furthest to the left is the least concentrated, whereas the right is the most. The one on the left has the least amount of Kool-Aid. The one on the right tastes the best because it has the most amount of Kool-Aid. The base unit for concentration is called a mole. Yes, like that kind of mole. All right. Then there's area and volume. Area is length times width. All right, and the unit is meters squared. And so if we were going to do the area of this here Rubik's Cube, it would be 123 by 123, or if those little things were meters, it would be 9 meters squared. Now volume is length times width times height, or length times width times height, 3 times 3 times 3, or 27 meters cubed. Meters cubed because it's 3 measurements versus 2. And then lastly is density. What is density? Well, you can see here, density is these different objects have different densities, and so after a little while they settle out, both the liquids and the solid things that are floating in there. Density is mass divided by volume, and it is in kilograms over meters cubed. Mass over volume. So this is the amount of something against its size. And so say, for instance, a marshmallow and a piece of steel of the same exact size. Which one is more dense? Of course, steel is. Even though they have the same size, there's a lot more steel inside that little thing than there is marshmallow inside that marshmallow. And so in a picture like this, the most dense things will go to the bottom, like the bolt. There you can see the bolt has gone all the way to the bottom, and the honey is the most dense liquid, whereas the lamp oil is the least dense liquid, even less dense than water. And here's a cherry tomato here that doesn't sink or doesn't float in water, but does float in dish soap. Here's a popcorn kernel. There's some other things in here. Apparently there's a dye in there. Oh, I see the little numbers in there. And so yeah, you can see this is a pretty neat experiment if you have lots of food coloring and lots of strange liquids and objects. All right, so precision versus accuracy. Two words that are often mixed up. Accuracy is the closeness of a measurement to the true value. The true value, we'll say in this picture, is the bullseye. Well, the closeness to the bullseye is, well, which one's the closest? Well, this one's the closest. This one's closer than the other ones. And so the closer you are to the bullseye, the more accurate you are. What is precision? Well, precision is the closeness of a group of measurements to one another. So for instance, this group of numbers or measurements here is not very accurate, but is extremely precise. This one here is both accurate and precise. So when we talk about precision in the labs, I want you to be precise in that you do everything the same way every time. Even if you're not very accurate, we're not going to be very accurate. We're all amateur scientists here. But I want us to be precise in what we're doing so that we get very similar measurements all the time. Now, switching gears a little bit, we're going to talk a little bit about metric conversions. Now, this is probably something you've had some familiarity with. And metric conversions are simply taking one unit and converting it to another in the metric system. And this is a picture that we will use. So I'll put that up there. You can pause it if you need to spend some time there. This is another picture that is very similar to that. Now, what I will do typically when I'm solving problems like this is I will simply write out these letters. Now these letters all mean something, and before you start to freak out on me, I will, let's see, this is the base unit here. I will explain these letters. The K means kilo, and this is 1,000, a kilometer, kiloliter. H is hecto, or 100. DA is deca, D-E-K-A, and deca is 10 times 10. So I can put that up here actually, times 1,000 times 100 times 10. And in the middle here is the base unit. This is either your meter, your gram, or your liter. Now I told you that kilogram was the base unit of SI. That's correct. But in this case, we're going to use the gram as the middle unit here, not as the base unit per se. A gram is really, really small, 1 gram is. But we're just going to use it as the center here. Well, as you get smaller, then the D stands for deci, and deci is 0.1 grams, centa 0.01, and milli 0.001, 1,000th. Now, one of the big areas of confusion here is the fact that meter and milli have the same abbreviation. Milli, or milli, it's a prefix. The word meter is an actual unit of measurement. So milli will always be in front of something. Meter can stand alone, or it can be prefixed like this: millimeter, or kilometer, or hectometer, or so forth. But there is no such thing as just milli. It has to be a milliliter, or a milligram, or a millimeter. It has to be a milli something. And so make sure you are not confused there. Now, how do we convert units? Well, this can be as complicated or as simple as you want it to be. We're going to try to make it easy. Notice what happens. As you go to the right, the numbers get smaller. As you go to the left, the numbers get bigger. So let's say if I wanted to, let's say I have 1 kilogram. And I wanted to convert that into, or I wanted to see how many grams is in 1 kilogram. Well, let's look at this visually. I think this may help. So, a kilogram, here's a dude, and he's going to pick up a kilogram of something. It's going to look like that. It's kind of a big block. All right. A gram of something is going to be so tiny that if it was in your hand, you wouldn't know that it was in your hand. Think like a shaving, like if you like if you've ever sharpened something that's made out of metal, shavings. Think like grabbing a pinch full of those shavings. That's a gram. Not heavy at all. All right. And so what do you expect to happen as we go from kilograms to grams? Are there more grams in a kilogram or less? How many times is that little dot going to fit in that cube? Well, it's going to fit in there a lot. So when we go using this same structure here, the same order, when we go from the right to the left, we're always going to multiply. That means the number is always going to get bigger. You can't multiply 2 numbers together and it gets smaller. If you want to try to prove me wrong, please do that. You can't. All right. If you go to the left, what are you going to do? Then you're going to divide. So In order to get from kilograms to grams, what do we have to do? We have to move 1, 2, 3 spaces. Did I do any witchcraft there? Did I do anything crazy? No, I just moved 3 spaces. Or you could look at it like this. It's times 1,000 the base. Right? So you multiply that's 1 times 1,000. But I like to move my decimal. So I'm going to take this 1. Where's the decimal on the number 1? It's right there. All right. If it helps you put 1.0, that's fine. Just do that. Well, up here again, I move 1, 2, 3 spaces to get to grams to the right. So what's my number going to do? It's going to get bigger. Watch this. 1, 2, 3 spaces. What goes here? Zeros. That decimal. Well, I don't want everything to move. That decimal just moved. All right. And so 1,000 grams. Let's do another one. All right. So let's say that we have 42 centiliters, and we want to figure out how many hectoliters that is. Well, let's get a visual on our headless dude down here. All right, he's straight ahead now. All right, and a centiliter is going to look like that, and a hectoliter is going to look something like that. So if I have 42 of these, how many of these is that? All right, it's a good question. Is the number going to get bigger or smaller? It's going to get a lot smaller. All right. There's not 4,200 of these inside that. Don't tell me that. All right. So what's going to happen here up here? Well, we're going to start. Let me see if I can get rid of our blue circles here. I can just move them. We're going to start here at the C. We're going to go to the H, and we're dealing with liters this time. All right. So we're going to move how many spaces? We're going to move 1, 2, 3, 4 spaces to the left. So we're dividing. The number's going to get a lot smaller. If you want to do it this way, 4 spaces is what? How many 4 zeros is 10,000? So you could divide 42 by 10,000 and you'd have the correct answer. However, the way I do this, and I think the easy way to do this, is to take this 42. Where's the decimal go? It goes right there. And we're going to move 4 places to the left. 1, 2, 3, 4. All right. Now here are some practice problems. And so I suggest you can pause this video and you could work on these if you'd like to do that. Now, sometimes you may be called to convert metric to English or English to metric. In this class, you will always be given a conversion rate. For instance, if I say how many liters or how many quarts are in 5 liters, well, you would just take 5 liters and multiply this times 5 as well. There's not going to be a lot of this in this class, and we're not going to spend any time on it. We may do a little bit of practice, but nothing crazy. But every time I ask you to do this, I'll always give you the actual conversion rates. And here's some metric to English problems if you want to check those out. All right. So real quick, graphs. Different kind of graphs we're going to use in this class. Bar graphs, which is what I see mostly from students when they come in my classroom. Bar graphs are used to count things. They're used to make comparisons for things. They're not used to track progression. We will not use bar graphs a lot in this class. Right? But you can see here, height and feet um, versus animals down here at the bottom. The diamondback is the tallest, even though I wouldn't think of a snake as being tall. A 12-foot tall snake would be quite scary. Line graphs are what we're going to spend a lot of our time using. A line graph tracks progression. You can see here at the bottom is time. On the right, on the y-axis, excuse me, are the number of wolves, and in this case, moose, and they are tracked over time. Their populations are tracked over time. We're going to spend a lot of time tracking things in here over time, and so we will use line graphs. Pie charts are used to compare a part with the whole. To compare a part with the whole. So the percentage contribution of daily caloric expenditure. 30% of that is active thermogenesis. Don't care that you know what that is right now. Well, we can compare that 30% to the rest of the 70%, what it's doing in daily caloric expenditure. A scatter plot. Scatter plots are used to determine relationships between two things that may or may not be related, and you can try to see if there is a relationship between them. The relationship between grade in class and hours in doing homework. Well, this seems to show that there is a relationship between those two things, a positive relationship. And so we'll look at scatter plots. Here are some tables, and real quick, what do we use? So the value of Greg's car, what would we use to show that? I think the best thing for that would be a line graph because it would show progression. What about this salespeople? These Buchanans and Callahans and DeValios, and well, the grand total's down here, and each one of them sold a part of the grand total, so perhaps a pie graph would be best. And then down here, fifth grade medal winners, gold doll, must be a different thing, silver and bronze, and you can compare the number of gold doll medal winners and silver and bronze winners, and this would be a great thing for a bar graph. All right, so next, mean, which is just average. You need to know how to do the average. There's a couple of average problems. I feel like you've probably had this before, but you can practice if you don't get the correct answer. Let me know, but you should be able to figure that out. Median, this is the middle value in a set of numbers. If you have 13 numbers, you'll take the 7th value because 7 is in the middle of those. There happens to be 7, 7, 15 values here, so you're going to take the 8th one. And then range is the amount between the highest and the lowest numbers. So then you would just find the lowest, you'd find the highest, subtract that, and that'd be the range in that.